Hello and welcome to Infinite Science. Before we begin, I want you to do something simple. Stand up for a moment. Feel your feet pressing against the floor. Notice the weight of your body, the gentle pull downward that you felt every single second of your entire life. Now, if you're holding something, a pen, a phone, anything, let it go. Watch it fall. That simple act, something so ordinary you've seen it a million times, is one of the most profound mysteries in the entire universe. And the strangest part? We still don't fully understand it. This is the story of gravity, not as a dry scientific formula, but as a question that has haunted humanity for centuries. A question that led us from falling apples to curved spacetime, from standing on Earth to understanding black holes, and ultimately to a revelation so strange that even today, our greatest minds cannot fully explain it. This is the story of how the universe really works. And I promise you, by the end of this journey, you'll never look at a falling object the same way again. You'll never stand on the ground without feeling the curvature of space-time beneath your feet. You'll understand that you're not just on Earth, you're falling through a curved four-dimensional fabric, held up only by the ground pushing against you. Let's begin at the beginning, with the most familiar force in your life. Let's start with what you know. Every morning, you wake up and you feel it. That sensation of weight, of being held against your bed. When you stand, your muscles work against something invisible, something that never stops, never rests, never takes a break. Gravity. Drop a stone and it falls. Always down, never up, never sideways, always toward the center of the Earth. Throw a ball into the air and no matter how hard you throw it, it curves back down. Jump and you return. The Earth holds you. For most of human history, this seemed obvious. Of course things fall down. Of course we stay on the ground. That's just how the world is. But think about what that really means. There is an invisible force right now, pulling on every atom in your body. You can't see it. You can't turn it off. You can't block it or shield yourself from it. It passes through walls, through steel, through your skin and bones, and it never weakens, never stops. Every object around you, your chair, your desk, the air molecules in the room, is being pulled toward the center of the Earth with perfect, relentless consistency. Stand by a window. Look outside. Every leaf on every tree, every bird in the sky, every cloud floating above, all held by gravity. The rain falls because of it. Rivers flow downhill because of it. Mountains rise and eventually crumble because of it. Your heart has to work against gravity to pump blood to your brain. Your bones are dense and strong because they've spent your entire life supporting your weight against gravity. Your sense of balance, your inner ear, detects gravity to tell you which way is up. You are shaped by this force, physically and in ways you never think about. And here's what makes it truly strange. You don't just experience gravity on Earth. Look up at the moon. It hangs in the sky night after night, tracing the same path around our planet. It never falls to Earth, but it never flies away either. It's caught in a perfect dance, orbiting endlessly. The tides in our oceans rise and fall because the moon pulls on the water. Millions of tons of seawater lifted by something invisible, something reaching across 384,000 kilometers of empty space. The sun, 150 million kilometers away, holds Earth in its orbit. Holds Mars, Jupiter, Saturn, all the planets, all the asteroids and comets in a cosmic choreography that has continued for billions of years. No chains, no strings, no physical connection, just this mysterious pull operating across the void. Think about the precision of it. Earth has been orbiting the sun for 4.5 billion years. 4 and a 500 million trips around our star, and we've never spiraled inward, never drifted away. The orbital dance is so precise that we can predict where Earth will be in its orbit 1,000 years from now, 10,000 years from now, 1,000,000 years from now. What kind of force can operate with that kind of consistency, that kind of mathematical perfection across distances so vast? Ancient humans noticed this, of course. They saw objects fall. They saw the moon and stars move across the sky. But they didn't see the connection. For thousands of years, the heavens and the earth were thought to be completely different realms, operating under different rules. The sky was eternal, perfect, unchanging. The earth was temporary, chaotic, mortal. Aristotle, the great Greek philosopher, taught that objects fell because they were seeking their natural place. Heavy things belonged down, so they moved downward. Light things belonged up, so they rose. Fire climbed toward the heavens. Rocks sank into the earth. It wasn't a force, it was simply the nature of things, returning to where they belonged. The celestial spheres, meanwhile, were made of a fifth element, quintessence perfect and incorruptible. They moved in perfect circles because circles were perfect shapes. There was no deeper reason, no mechanism. That's just how the heavens worked. The moon, the sun, the planets, they were embedded in crystalline spheres that rotated around the Earth. The spheres were real, physical objects, though made of some perfect transparent material, unlike anything on Earth. For nearly 2,000 years, this was accepted wisdom. The terrestrial and celestial realms were separate, fundamentally different, governed by different principles. Medieval scholars refined Aristotle's ideas, building elaborate models of nested spheres, calculating the motions of planets with increasing sophistication. But the basic assumption remained: the heavens and Earth were different. They had no idea that the same force making an apple drop from a tree was the same force holding the moon in the sky, the same force governing the orbits of distant planets. It would take one brilliant, obsessive mind to see that connection. And when he did, everything changed. But before we meet that mind, we need to understand something else. We need to understand that gravity isn't just about falling. It's about motion itself, about the paths objects trace through space, about the invisible architecture that shapes the universe. England, 1666. A young man sits in a garden in Woolsthorpe, Lincolnshire. The plague has swept through London, and Cambridge University, where he studies, has closed. Isaac Newton, just 23 years old, has returned to his family's estate, and he is thinking. He's thinking about the moon. The popular story says an apple fell from a tree and hit him on the head, giving him a sudden insight. That's probably not true, but something like it might have happened. Newton himself wrote later that he was indeed contemplating the fall of an apple while considering the motion of the moon. And here's the question that changed everything. Why does the apple fall, but the moon doesn't? The apple drops straight down, accelerating as it falls, picking up speed until it hits the ground with a thud. The moon stays up, circling the Earth, never falling, never escaping. They seem completely different. But Newton had a wild thought. What if they're not different at all? What if the moon is falling? Think about it. When you throw a ball, it curves downward as it flies, pulled by gravity. Throw it faster and it goes farther before it hits the ground. Throw it from a mountain and it goes even farther. The curve of its path gets flatter, more horizontal, but it always comes down. Now imagine throwing it impossibly fast, so fast that by the time it falls a meter, the curved surface of the Earth has dropped away beneath it by a meter. The ball would fall and fall, but never hit the ground. It would be in orbit, That's what the moon is doing. It's constantly falling toward Earth, but it's also moving sideways so fast, about 1 kilometer per second, that it keeps missing. It's in perpetual freefall, forever tumbling through space, forever held by the same force that makes an apple drop. Newton realized something extraordinary. The force pulling the apple and the force holding the moon are the same force. Gravity doesn't stop at the treetops. It doesn't stop at the clouds or the edge of the atmosphere. It extends out into space, reaching the moon, the planets, the sun, everything. But he went further, much further. He worked out the mathematics. He showed that every object in the universe attracts every other object with a force that depends on their masses and the distance between them. More mass means stronger pull. Greater distance means weaker pull. Specifically, the force drops off with the square of the distance, double the distance, and the force becomes 4 times weaker. Triple the distance, 9 times weaker. This is called the inverse square law, and it's beautiful in its simplicity. The formula was elegant, universal, and it explained everything anyone had ever observed about motion, both on Earth and in the heavens. With this one insight, Newton explained phenomena that had puzzled humanity for millennia. Why do planets orbit the sun in ellipses, as Johannes Kepler had observed decades earlier? Because they're following the paths dictated by the sun's gravity and the inverse square law. The elliptical orbits aren't arbitrary, they're the natural consequence of an inverse square force. Why do the inner planets orbit faster than the outer planets? Because they're deeper in the sun's gravitational well, feeling a stronger pull. Mercury completes an orbit in just 88 Earth days, while Neptune takes 165 Earth years. Why do moons orbit planets? Same reason, gravity. Jupiter has 95 known moons, all held in orbit by Jupiter's gravity, each following its own elliptical path. Why do the tides rise and fall twice a day? The moon pulls on the water in Earth's oceans. The side facing the moon is pulled more strongly than Earth's center, and Earth's center is pulled more strongly than the far side. This creates 2 bulges of water, one facing the moon and one on the opposite side. And as Earth rotates beneath these bulges, we experience high tide twice a day. The sun also contributes to tides. When the sun and moon align, during new moon or full moon, their gravitational pulls add together, creating extra high spring tides. When they're at right angles during quarter moons, they partially cancel, creating smaller neap tides. Why do cannonballs and arrows curve through the air? Gravity pulls them down even as they move forward, creating parabolic arcs. Why do we stay on the ground? Earth's gravity pulls us toward its center. Why can buildings only be built so tall before they collapse? The strength of materials has limits, and gravity creates stress that eventually exceeds those limits. On a planet with weaker gravity like Mars, you could build structures 3 times taller before they'd collapse under their own weight. For the first time in human history, the heavens and Earth were united under one law. The same force that made an apple fall explained the orbit of the moon, the motion of the planets, the tides, everything. It was revolutionary. It was beautiful, and it worked perfectly. Astronomers used Newton's laws to predict the positions of planets decades in advance, and the predictions were correct down to the arc second. When Uranus's orbit showed slight deviations from Newton's predictions, astronomers hypothesized that there must be another planet, farther out, tugging on Uranus with its gravity. They used Newton's laws to calculate where that planet should be based on the deviations they observed. And when they pointed their telescopes to the predicted location in 1846, there it was, Neptune, exactly where the mathematics said it should be. That discovery, finding a planet with mathematics before seeing it with a telescope, was one of the greatest triumphs of Newtonian physics. It showed that Newton's laws weren't just descriptions of what we'd already seen. They were tools for predicting new discoveries. Engineers used Newton's laws to build machines, to calculate trajectories, to understand motion, stress, and structure. The entire Industrial Revolution was built on Newtonian mechanics. Bridges, railways, factories, engines, all designed using Newton's laws of motion and gravity. When the Wright brothers designed their first airplane, they used Newtonian physics to calculate lift and drag. When NASA sent astronauts to the moon, they used Newton's laws to calculate trajectories, though they also had to include small relativistic corrections we'll discuss later. Newton's gravity became the foundation of physics, the bedrock of our understanding of the universe. Scientists spoke of it with reverence. It was considered complete, final, the ultimate answer to one of humanity's oldest questions. Newton himself was elevated to near mythical status. Alexander Pope wrote, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." For more than 2 centuries, Newton's law of gravity stood unchallenged. It was tested again and again in every conceivable situation, and it always worked. Every measurement, every observation, every prediction confirmed Newton's inverse square law. But there was a problem, a small crack in the foundation that Newton himself had noticed and worried about. And if you looked closely enough at that crack, you'd realize that Newton's beautiful theory had left one crucial question completely unanswered. A question that would eventually topple the entire edifice and replace it with something even stranger. Newton's law of gravity told us what happens. It didn't tell us why. Objects attract each other. Fine, but how? Think about it. You're sitting on Earth right now. The sun is 150 million kilometers away. There's nothing between you and the sun but empty space. Vacuum, void, nothingness. No air, no substance, no medium of any kind. And yet, somehow, across all that emptiness, the sun reaches out and pulls on you. On Earth. On every atom of our planet. How does it do that? Newton himself was deeply troubled by this question. He couldn't explain it, and it bothered him for the rest of his life. In his own words, he called the idea of action at a distance. 2 objects influencing each other without touching, without any physical connection. Absurd. And yet, his equations demanded it. He wrote, "That one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it." Strong words from the man who discovered universal gravitation. And yet, that's exactly what his theory required. Imagine you're floating in space, far from any planet or star. You're alone in the darkness. Suddenly, a massive star appears 1 billion kilometers away. Instantly, according to Newton, you feel its gravity. Instantly, you begin to fall toward it, even though there's nothing connecting you. No chain, no field, no physical medium carrying the force. How does the star know you're there? How does the information travel? What carries the force across the void? Newton had no answer. He admitted as much. His law described gravity's effects with perfect accuracy, but it said nothing about the mechanism. It was a recipe without ingredients, a map without terrain. He wrote to a colleague, "I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses." In other words, I don't know how it works. I can describe what it does, but I can't tell you why or how. I refuse to make up explanations without evidence. This was intellectually honest, but it left a gaping hole in the theory, and Newton knew it. Some of Newton's contemporaries and successors tried to fill this hole. They proposed that space was filled with an invisible substance, an ether that transmitted gravitational force the way air transmits sound. But there was no evidence for such a substance, and every attempt to detect it failed. René Descartes had earlier proposed that space was filled with invisible vortices that carried planets around the sun. But this couldn't explain Kepler's laws or produce quantitative predictions. Newton's inverse square law worked. The vortex theory didn't. And there was another problem, one that wouldn't become apparent until much later, until physics had advanced far beyond Newton's time. According to Newton, gravity acts instantaneously. If the sun suddenly vanished, just blinked out of existence, Earth would immediately fly off into space. There would be no delay, no travel time for the gravitational signal. The change would propagate instantly across 150 million kilometers of space. Faster than light, infinitely fast. Even in Newton's time, this seemed strange. But there was no way to test it, no way to make the sun vanish. And the theory worked so well in every other respect that physicists simply accepted it as a quirk, an unexplained feature of how gravity works. But as physics progressed through the 18th and 19th centuries, as scientists learned more about light, electricity, and magnetism, the instantaneous action problem became more troubling. In the 1860s, James Clerk Maxwell unified electricity and magnetism into a single theory, electromagnetism, and showed that light is an electromagnetic wave. His equations revealed that electromagnetic changes propagate at a finite speed, about 300,000 kilometers per second. Fast, but not infinite. If you wiggle an electron here, the electromagnetic field change takes time to reach a distant observer. The information travels at the speed of light. If electromagnetic forces propagate at the speed of light, why should gravity be different? Why should gravity alone act instantaneously? Some physicists tried to create theories of gravity that propagated at the speed of light, using equations similar to Maxwell's. But these attempts ran into problems. They couldn't reproduce Newton's successful predictions while also having gravity propagate at finite speed. The puzzle deepened. But Newton didn't live to see this problem become a crisis. That would take another genius, another revolution, and a completely different way of thinking about reality itself. For 200 years, physicists used Newton's laws without worrying too much about the mechanism. They worked. The predictions matched observations. That was enough for practical purposes. Until a young patent clerk in Switzerland started thinking about light, time, and the nature of space itself. His name was Albert Einstein, and he was about to overturn everything we thought we knew about gravity, space, and time. But before we meet Einstein, we need to understand something else that emerged in the 19th century, something that would prove crucial to Einstein's breakthrough, a tiny discrepancy that nobody could explain. By the late 19th century, Newton's laws had been tested extensively across the solar system, and they worked almost perfectly. Almost. There was one tiny discrepancy, one small observation that didn't quite match Newton's predictions. Mercury, the innermost planet, orbits the Sun in an ellipse. But that ellipse doesn't stay fixed in space. It rotates very slowly, like a spinning flower petal. This is called precession. The axis of the ellipse shifts, causing Mercury's closest approach to the Sun to occur at a slightly different point in space with each orbit. Newton's laws predict precession. The gravitational tugs from other planets, Venus, Earth, Jupiter, Saturn, pull on Mercury's orbit, causing it to precess. And when astronomers calculated the expected precession using Newton's laws, accounting for all the planets, they got 531 arc-seconds per century. An arc-second is tiny, 1/36th of a degree. So 531 arc-seconds is about 0.15 degrees per century. Still, with careful measurements over decades, astronomers could measure this precisely. When they measured the actual precession, they got 574 arc-seconds per century. The difference was 43 arc-seconds per century. Tiny, less than 1/100th of a degree per century. But it was real, reproducible, and it was unexplained. For decades, this tiny discrepancy puzzled astronomers. They tried everything to explain it. Maybe there was another planet, even closer to the Sun than Mercury, pulling on Mercury's orbit. They called this hypothetical planet Vulcan and searched for it during solar eclipses, when a planet close to the Sun might become visible. They never found it. Vulcan doesn't exist. Maybe Newton's inverse square law was slightly wrong. Maybe gravity doesn't fall off exactly with the square of the distance. But changing Newton's law to explain Mercury would break all the other predictions that worked perfectly for the other planets. Maybe there was a ring of dust or asteroids close to the Sun, creating extra gravitational pull. But no such ring was observed, and calculations showed it couldn't produce the observed effect. For decades, this tiny discrepancy, 43 arc-seconds per century, remained unexplained, a small crack in the otherwise perfect edifice of Newtonian gravity. Some physicists thought it must be a measurement error, that better observations would make the discrepancy disappear. Others thought there must be some subtle effect they were missing, some small correction to the calculations. Nobody suspected that the problem was fundamental, that Newton's entire framework was incomplete, that a revolution was coming. And when Einstein finally published his theory of general relativity in November 1915, one of the first things he did was calculate Mercury's orbit using his new equations. The theory predicted exactly 43 arc-seconds per century of extra precession, not approximately, exactly, to the precision of measurement. Einstein didn't add any fudge factors, didn't adjust anything to make it fit. The precession fell out of the equations naturally, automatically, as a consequence of curved spacetime near the Sun. When Einstein got the result, he was so excited he had heart palpitations. He later said it gave him the feeling that something actually snapped in him. It was one of the most thrilling moments of his scientific life. That tiny discrepancy in Mercury's orbit, ignored or explained away for decades, was the first evidence that Newton's gravity wasn't quite right, that there was something deeper going on, that the universe was stranger than anyone had imagined. But we're getting ahead of ourselves. Let's go back to 1907 to Einstein sitting at his desk in Bern, thinking about gravity and having the happiest thought of his life. Switzerland, 1907. Albert Einstein is sitting at his desk in the patent office in Bern. He's been thinking about gravity for years now, and he's hit a wall. 2 years earlier, in 1905, his miracle year, he published 4 groundbreaking papers, including his theory of special relativity. Special relativity showed that space and time are connected, woven together into a single fabric called spacetime. It showed that nothing can travel faster than light, that simultaneity is relative. Events that appear simultaneous to one observer might not be simultaneous to another. That time itself can slow down or speed up depending on how fast you're moving. The theory was revolutionary, strange, counterintuitive. But the mathematics worked, and experiments would later confirm every prediction. But gravity doesn't fit into this beautiful new framework. According to Newton, gravity acts instantly. If the sun vanished, Earth would immediately fly off into space. According to Einstein's own theory of special relativity, that's impossible. Nothing, no force, no signal, no information, can travel faster than light. Something has to give. Einstein wrestles with this problem for years. He tries various approaches, explores different mathematical frameworks, but nothing works. Gravity remains stubbornly incompatible with special relativity. And then, sitting at his desk, he has what he'll later call the happiest thought of my life. He imagines a man falling off a roof. During the fall, before he hits the ground, the man feels weightless. He doesn't feel gravity. If he pulls objects from his pockets and releases them, they float beside him, falling at the same rate he is. Einstein realizes the man is in freefall, and in freefall, gravity seems to disappear. This is the key. This is the insight that will unlock everything. Now imagine you're standing in an elevator. Normal elevator, nothing special. You feel your weight, the floor pressing against your feet, gravity holding you down. Now imagine the cable snaps and you start to fall. What would you feel? Nothing. You wouldn't feel heavy. You wouldn't feel the floor pressing against your feet. You'd float, weightless, falling alongside the elevator. If you let go of your phone, it would hover next to you, falling at the same rate you are. You could push off the walls and drift through the air. Inside that falling elevator, you'd feel exactly the same as an astronaut in space, far from any planet, drifting in zero gravity. Now flip the scenario. Imagine you're in that same elevator, but now it's in deep space, far from any star or planet. No gravity. You're floating, weightless. Suddenly, a rope attached to the top of the elevator starts pulling it upward, accelerating at exactly 9.8 meters per second squared, the same acceleration you experience from Earth's gravity. What would you feel? You'd feel your feet press against the floor. You'd feel weight. If you dropped something, it would fall to the floor. If you jumped, you'd come back down. You couldn't tell the difference between being pulled upward in space and standing on Earth. You couldn't perform any experiment inside the elevator, no measurement, no observation that would tell you whether you're accelerating in space or standing in a gravitational field. You couldn't tell the difference because there is no difference. Einstein realized something profound. Acceleration and gravity are the same thing. Locally, in a small enough region of space, they're completely indistinguishable. This is called the equivalence principle, and it's the cornerstone of everything that follows. When you're standing on Earth, you're not being pulled down by a mysterious force. You're being pushed up by the ground beneath you. The Earth's surface is accelerating upward into you, pressing against your feet, holding you. Wait, you might think. That doesn't make sense. The Earth isn't accelerating, it's just sitting there. We can measure it. It's not moving upward. That's absurd. And that's where Einstein made his leap into something completely new, something that would require rethinking the very nature of space and time. What if space itself is curved? Imagine a trampoline, stretched tight and flat. The surface is two-dimensional, but it exists in three-dimensional space, so it can curve. Now, place a bowling ball in the center. The fabric dips, curves around the ball, creating a bowl-shaped depression. If you roll a marble near the edge, it will curve inward, spiral around the bowling ball, maybe even orbit it for a while before falling in. The marble isn't being pulled by the bowling ball. There's no invisible force reaching out and grabbing it. The marble is simply following the curved surface. It's moving in a straight line, or rather, the straightest possible line it can follow on the curved surface. But because the surface itself is curved, the straight line curves. That's what mass does to space-time. But here's where the analogy becomes limited and we need to think more carefully. The trampoline analogy uses gravity to show how gravity works, which is circular. In reality, it's not space alone that curves, it's space-time, the four-dimensional fabric that combines the three dimensions of space with the one dimension of time. This is hard to visualize because we're three-dimensional creatures trying to picture four-dimensional geometry. But the mathematics is clear. The sun doesn't pull on Earth. The sun curves the space-time around it, and Earth follows that curve. The Earth isn't held in orbit by an invisible force. It's moving through curved space-time, following the straightest possible path, what mathematicians call a geodesic, in a universe that isn't flat. A geodesic is the generalization of a straight line to curved spaces. On a flat piece of paper, the shortest distance between 2 points is a straight line. On the curved surface of Earth, the shortest distance between two cities is a great circle arc. That's why airplane routes look curved on flat maps. In curved spacetime, geodesics are the paths that objects follow when no forces act on them. Planets orbiting the Sun are following geodesics. The Moon orbiting Earth is following a geodesic. A falling apple is following a geodesic. You're not being pulled down by Earth's gravity. You're trying to move through curved spacetime following your natural geodesic, and the ground is in your way, pushing you upward, preventing you from following your natural path through the curved geometry. Think about what this means. When you're standing still on Earth, you're actually accelerating upward. The ground is pushing you up at 9.8 meters per second squared, preventing you from following the natural curve of spacetime. When you jump, you briefly follow that natural curve. You're in freefall, following a geodesic through curved spacetime. Then the ground gets in your way again, and you stop. Gravity isn't a force, it's geometry. When you drop something, it's not being pulled. It's following the curve of spacetime, falling along the natural path created by Earth's mass. When you orbit a planet, you're not being held by a force. You're moving in a straight line through curved space, except straight in curved space looks curved to us. Einstein spent 8 years working out the mathematics, turning this insight into a complete theory. The equations were fiendishly difficult. 10 interrelated partial differential equations describing how matter and energy curve spacetime and how that curvature dictates the motion of matter and energy. He later called them the most difficult work of his life. The mathematics required was far beyond what physicists typically used. He enlisted help from his mathematician friend Marcel Grossmann to work out the tensor calculus needed to express the ideas precisely. Einstein struggled with different versions of the equations, publishing preliminary versions that turned out to be incorrect. Other physicists, notably David Hilbert, were working on similar problems. For a brief period in November 1915, it wasn't clear who would publish the correct equations first. Finally, on November 25, 1915, Einstein presented the complete correct field equations to the Prussian Academy of Sciences in Berlin. These equations, now called the Einstein field equations, describe how mass and energy curve spacetime and how that curvature affects the motion of matter and energy. The equations are elegant in their symmetry, though forbiddingly complex in their details. On one side, they describe the curvature of spacetime. On the other side, they describe the distribution of matter and energy. The equal sign in the middle says, these two things are the same. Mass energy tells spacetime how to curve. Spacetime curvature tells matter how to move. And when he did the calculations, he didn't just explain gravity. He revealed that space and time themselves are dynamic, flexible, woven together into a single fabric that bends and warps and ripples in response to matter and energy. The universe isn't a stage on which events happen. The universe is the events, and the stage itself is dynamic, changing, responsive to what's happening on it. Suddenly, Newton's mystery, how gravity works across empty space, wasn't a mystery anymore. There is no pull across the void. Space itself carries the information. Mass tells space-time how to curve. Space-time tells matter how to move. It was beautiful. It was elegant. And almost immediately, Einstein's theory made predictions that Newton's couldn't. It explained Mercury's extra precession, those mysterious 43 arc-seconds per century that had puzzled astronomers for decades. It predicted that light should bend in gravitational fields, and not just a little, but twice as much as Newton's theory suggested. It predicted that time should slow down in gravitational fields, that clocks at different altitudes should run at different rates. It predicted entirely new phenomena, gravitational waves, ripples in space-time itself propagating at the speed of light. Black holes, regions where space-time curves so sharply that not even light can escape. The expansion or contraction of the universe itself. It was time to test these predictions. And the first opportunity came just 4 years later, with a total solar eclipse. If space-time is curved by mass, then everything moving through space should follow that curve. Not just planets and apples and moons, light too. Light has no mass, or at least no rest mass. In Newton's framework, that meant gravity shouldn't affect light at all, or affect it only infinitesimally. But in Einstein's framework, light travels through space-time, and if space-time is curved, then light should curve along with it. It should follow the geodesics of curved space-time, just like everything else. Actually, Newton's theory did predict a small deflection of light in a gravitational field. If you thought of light as made of particles with tiny mass, Newton's laws suggested they'd be deflected by about 0.87 arc-seconds at the edge of the Sun. But Einstein's theory predicted twice as much, 1.75 arc-seconds. The difference was subtle but measurable with the telescopes and photographic equipment available in 1919. In 1919, just 4 years after Einstein published his theory, astronomers had a chance to test this. A total solar eclipse was coming on May 29th, and during those precious minutes of darkness, stars near the Sun would become visible against the darkened sky. If Einstein was right, the Sun's mass would curve space-time around it, and light from those background stars would bend as it passed by. The stars would appear to be in slightly different positions than they actually were, shifted outward, away from the Sun, by a measurable angle. If Newton's prediction was correct, the shift would be half as large. If neither theory was right, the stars might not shift at all. Arthur Eddington, a British astronomer and one of the few scientists who fully understood Einstein's theory, led expeditions to Príncipe Island off the coast of Africa and to Sobral, Brazil, to photograph the eclipse. The stakes were enormous. Einstein's entire theory rested on this test. The timing was also significant. World War I had just ended the previous year. Einstein was German, working in Berlin. Eddington was British. And here was a British scientist traveling halfway around the world to test a German scientist's theory, just months after the most devastating war in human history. It was a moment of international scientific cooperation in the aftermath of terrible conflict. A demonstration that science transcends national boundaries, that the pursuit of truth can unite people even when politics divides them. The expeditions faced significant challenges. The weather had to cooperate. Clouds would ruin everything. The photographic plates had to be perfect. The measurements had to be extraordinarily precise, comparing the positions of stars during the eclipse to their positions at other times of the year. The day came. May 29th, 1919. The moon slid in front of the sun. For a few brief minutes, stars appeared around the darkened solar disk. Photographs were taken on glass plates, capturing the positions of stars near the sun's limb. Then the moment passed, and the teams packed up their equipment. It took months to analyze the photographic plates, to measure the precise positions of the stars using micrometers, to account for atmospheric distortion, lens aberrations, temperature effects on the photographic emulsion, and all the other factors that could introduce error. The measurements were at the very edge of what was technically possible at the time. There were sources of systematic error that had to be carefully considered. Some of the plates were better than others. Some had been affected by clouds or poor focus. When the results finally came back and were announced on November 6th, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London, they were clear. The starlight had bent. About 1.75 arc seconds at the edge of the sun, give or take the measurement uncertainty. Exactly as Einstein predicted, twice as much as Newton's theory suggested. The announcement was dramatic. The meeting took place in the hall where Newton's portrait hung on the wall. J. Thomson, the president of the Royal Society and discoverer of the electron, declared it one of the highest achievements of human thought. The philosopher Alfred North Whitehead, who attended the meeting, later wrote that the atmosphere was exactly that of Greek drama. There was a sense that the greatest possible overthrow of the accepted scientific ideas had occurred. Overnight, Einstein became the most famous scientist in the world. Headlines screamed, "Lights all askew in the heavens. Revolution in science. Newtonian ideas overthrown." The Times of London proclaimed, "Revolution in science, new theory of the universe. Newtonian ideas overthrown." The New York Times headline read, "Lights all askew in the heavens. Men of science more or less, agog over results of eclipse observations. Einstein theory triumphs." Einstein, who had been working in relative obscurity for years, became a global celebrity almost overnight. People wanted to understand this new, strange theory that had overthrown Newton. Einstein was invited to give lectures around the world. His name became synonymous with genius. Reporters asked him to explain relativity in simple terms. He gave them sound bites. Put your hand on a hot stove for a minute, and it seems like an hour. Sit with a pretty girl for an hour, and it seems like a minute. That's relativity. The public fascination was extraordinary. Relativity captured the imagination like few scientific theories before or since. It was strange, counterintuitive, and it had just been confirmed by bending starlight. The universe had confirmed it. Space-time was real. Gravity was curvature. Reality itself was stranger than anyone had imagined. And this wasn't just a small effect, visible only in careful measurements during rare eclipses. Gravity bends light in ways we can see across the universe, creating some of the most spectacular phenomena in astronomy. Imagine a galaxy far away, billions of light years from Earth. Now imagine another massive galaxy or cluster of galaxies between us and that distant one, lying almost perfectly in our line of sight. The closer galaxy's mass curves space-time around it, creating what we call a gravitational lens. Light from the distant galaxy bends as it passes through this curved region. Multiple light paths can reach Earth, coming from different angles around the lensing galaxy. From Earth, we might see multiple images of the distant galaxy, distorted and stretched into arcs or rings. Sometimes we see the same galaxy in 4 different places at once, a phenomenon called an Einstein cross. It's light taking 4 different curved paths around the intervening mass. Sometimes, if the alignment is perfect, we see an Einstein ring, a perfect circle of light surrounding the lensing galaxy, the distant galaxy's light bent into a complete ring by the curved spacetime. The first gravitational lens was discovered in 1979, twin images of a distant quasar called Q0957+561, created by an intervening galaxy. At first, astronomers thought they were looking at two separate quasars. But the spectra were identical, and they varied in brightness in exactly the same way, with one image delayed slightly in time because its light path was longer. They were seeing the same object twice, its light bent around a gravitational lens. Since then, thousands of gravitational lenses have been found, strong lenses that create multiple images, weak lenses that slightly distort the shapes of background galaxies, microlensing events where a nearby star passes in front of a more distant star, temporarily brightening it as the closer star's gravity focuses the light. This is called gravitational lensing, and it's one of the most stunning confirmations of Einstein's theory. We use it now as a tool, a natural telescope. We find distant galaxies we could never see otherwise, magnified by the curved spacetime of intervening matter. We map dark matter, invisible mass that we can't see directly but that reveals itself by bending light. By carefully measuring how background galaxies are distorted, we can create maps of dark matter distribution, revealing the invisible scaffolding of the cosmos. Some of the most distant galaxies ever observed were only detectable because gravitational lensing magnified their light by factors of 10, 20, even 50 times. The Hubble Space Telescope and now the James Webb Space Telescope routinely use massive galaxy clusters as natural telescopes, peering through these cosmic magnifying glasses to see galaxies from the early universe. Some formed less than 1 billion years after the Big Bang. In 2019, the Event Horizon Telescope, a network of radio telescopes around the world working together, captured the first image of a black hole's shadow, specifically the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. In that image, you can see the shadow of the black hole, a dark circle, surrounded by a bright ring of light. That ring is created by light from hot gas, orbiting the black hole at nearly the speed of light, bent around the black hole by the extreme curvature of space-time. Some of that light has orbited the black hole multiple times before escaping, creating the bright photon ring. Every time we see gravitational lensing, every time we observe light bent by gravity, we're seeing direct evidence that space-time is curved, that Einstein was right. But gravity doesn't just bend space, it bends time. This is perhaps the strangest consequence of general relativity, and it's one that affects your daily life, even if you don't realize it. Picture two identical clocks, perfect atomic clocks that keep time with extraordinary precision, measuring time by counting the oscillations of cesium atoms. About 9 billion oscillations per second. Place one on the ground and one on top of a mountain. Leave them running for a year, then bring them back together and compare them. The clock on the mountain will be ahead. Not by much, just about 30 nanoseconds for every meter of altitude difference, accumulated over a year, but measurably, detectably ahead. Why? Because time moves slower in stronger gravity. The clock on the ground, deeper in Earth's gravitational well, deeper in the curve of space-time, experiences time more slowly than the clock at higher altitude. This isn't a defect in the clocks. This isn't an optical illusion or a measurement error. Time itself is running at different rates in different gravitational fields. Einstein's equations predict this precisely. The stronger the gravity, the slower time flows. Near a massive object, time slows down. Far from massive objects, time speeds up. This effect is called gravitational time dilation, and it's been measured countless times with extraordinary precision. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners and compared them to clocks that stayed on the ground. The flying clocks farther from Earth's center and in a weaker gravitational field gained time, exactly as Einstein predicted. There was also a special relativistic effect. Because the clocks were moving, time ran slower for them. But the gravitational effect was larger and easier to measure. Atomic clocks at different altitudes in the same building run at different rates. Clocks at the National Institute of Standards and Technology in Boulder, Colorado, can detect the difference in gravitational time dilation between two clocks separated vertically by just 1 centimeter. 1 centimeter. The difference in time flow over a height difference smaller than your hand is measurable with modern atomic clocks. GPS satellites orbiting Earth have to account for this. They're about 20,000 kilometers above Earth's surface, so they're in a weaker gravitational field than we are on the ground. According to general relativity, time runs about 45 microseconds per day faster for them than it does for us on the surface. There's also a special relativistic effect because the satellites are moving at about 14,000 kilometers per hour relative to Earth's surface. Time runs slower for them by about 7 microseconds per day. The total effect is about 38 microseconds per day faster for the satellite clocks. That might not sound like much, but GPS works by measuring the time it takes for radio signals to travel from satellites to your receiver. Those signals travel at the speed of light, 300,000 kilometers per second. A timing error of 38 microseconds corresponds to a position error of about 11 kilometers. If we didn't correct for both special and general relativistic time dilation, GPS coordinates would drift by about 10 kilometers per day. After a few days, GPS would be completely useless. Every time you use GPS to navigate, every time your phone tells you where you are, every time you get turn-by-turn directions, you're relying on corrections for both special and general relativity. You're relying on our understanding of curved spacetime and time dilation. Think about what this means. Gravity doesn't just tell objects how to move. It doesn't just bend the paths of light. It changes the flow of time itself. Your head ages faster than your feet because it's slightly farther from Earth's center in a slightly weaker gravitational field. The difference is tiny, nanoseconds over a lifetime. But it's real. Over your entire life, your head will be about 90 nanoseconds older than your feet. Time is not absolute. It's not a universal clock ticking at the same rate everywhere in the universe. It's part of the fabric of space-time, and it warps and bends along with space. Near a massive object like the Sun, time runs about 99.9999978%, as fast as it does far from any mass. The difference is tiny but measurable. Near a white dwarf star, a collapsed stellar remnant about the size of Earth but with the mass of the Sun, time runs about 99.97% as fast. The gravitational redshift of light from white dwarfs has been measured and matches Einstein's predictions. Near a neutron star, even more compact with a radius of just 10 to 20 kilometers, but twice the mass of the Sun, time runs significantly slower, perhaps 70 to 80% as fast. And if you want to see this taken to its extreme, if you want to witness what happens when space-time curves so sharply that our everyday intuitions completely break down, when time dilation becomes so severe that it approaches infinity, you need to go to the strangest, most extreme objects in the entire universe. You need to go to a black hole. Imagine a star, a massive star, 20 or 30 times heavier than our Sun. For millions of years, it burns, fusing hydrogen into helium in its core, helium into carbon, carbon into oxygen, nitrogen, silicon, iron. The nuclear fusion releases energy, creating heat and pressure that push outward, balancing the inward crush of gravity. It's a delicate equilibrium. The star lives in tension between two forces, gravity trying to collapse it, and nuclear fire holding it up. But eventually, inevitably, the fuel runs out. Iron accumulates in the core. Iron is the end of the line. It's the most stable nucleus sitting at the bottom of the nuclear binding energy curve. Fusing iron doesn't release energy, it absorbs energy. The nuclear fires sputter and die. Suddenly, there's nothing pushing outward, nothing to balance gravity. When there's nothing left to burn, nothing to push back against the relentless inward crush, the core collapses. Suddenly, catastrophically. In less than a second, often in less than a tenth of a second, the core implodes. Millions of kilometers of stellar matter falls inward. The outer layers of the star, robbed of support, fall inward at speeds approaching a quarter of the speed of light, reaching temperatures of billions of degrees, then rebound in the most violent explosion in the universe. A core collapse supernova. For a few weeks, that single dying star can outshine an entire galaxy of hundreds of billions of stars. It can briefly outshine the rest of the observable universe combined. New elements are forged in the explosion: gold, platinum, uranium, all the heavy elements beyond iron in the periodic table. These are scattered into space, seeding future generations of stars and planets. Every gold atom in your wedding ring, every uranium atom in nuclear fuel was forged in a supernova explosion. But while the outer layers explode outward, scattering newly forged elements into space at thousands of kilometers per second, the core keeps falling. It falls inward, compressing, squeezing atoms together, crushing electron shells, overcoming electron degeneracy pressure. Protons and electrons are forced together, merging into neutrons and releasing neutrinos, ghostly particles that barely interact with matter and stream outward, carrying away enormous amounts of energy. The core shrinks from the size of Earth to the size of a city in less than a second. The density becomes unimaginable. A sugar cube-sized piece of this material would weigh as much as all of humanity combined, about 500 million tons. This is a neutron star, one of the densest objects in the universe. The gravity at its surface is so strong that a mountain on a neutron star would be less than a centimeter tall, squashed, flat by gravity hundreds of billions of times stronger than Earth's. A neutron star is held up by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being squeezed any closer together. For stellar cores up to about 2 to 3 times the mass of the Sun, neutron degeneracy pressure is enough to halt the collapse. But if there's enough mass, if the star was massive enough, even neutron degeneracy pressure can't hold up the core. Nothing can. No known force, no known state of matter can withstand the crushing weight. The collapse doesn't stop. It keeps falling, keeps compressing, beyond the neutron star phase, beyond any known state of matter, until it becomes a point, a singularity, a place where all the mass is concentrated into zero volume, where density becomes infinite, where the curvature of spacetime becomes so extreme that our equations break down and scream. Around this singularity, there's a boundary, a point of no return. Cross this boundary, and you can never come back. The curvature of spacetime is so extreme that all paths, all geodesics, all possible futures lead inward. Even light, traveling at the ultimate speed limit of the universe, can't escape. We call this boundary the event horizon. This is a black hole. The term black hole was coined by physicist John Wheeler in 1967, But the concept is much older. In 1916, just months after Einstein published general relativity, German physicist Karl Schwarzschild found an exact solution to Einstein's equations, describing the spacetime around a perfectly spherical, non-rotating mass. Schwarzschild found that if you compress enough mass into a small enough space, if you squeeze it inside what's now called the Schwarzschild radius, you get an event horizon and a singularity. For the Sun, the Schwarzschild radius is about 3 kilometers. If you could compress the Sun to a ball 6 kilometers across, it would become a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. Compress Earth to the size of a marble, and it becomes a black hole. Schwarzschild found this solution while serving in the German army during World War I, doing calculations in the trenches. He sent his paper to Einstein from the Russian front. Ironically, Schwarzschild died of a disease contracted at the front just a few months later, never knowing that his solution would become one of the most important in all of physics. For decades, most physicists thought black holes were mathematical curiosities, not real objects. Even Einstein was skeptical. The idea seemed too extreme, too bizarre. But in the 1960s and 70s, as astronomers found compact X-ray sources and quasars, objects of extraordinary luminosity, physicists realized black holes were not only possible, but probably common. Today, we know that most large galaxies, including our own Milky Way, have supermassive black holes at their centers. Let's imagine you're approaching a black hole. Not a small, stellar mass, black hole. Those are more violent, more extreme, with stronger tidal forces. Let's make it big, supermassive, millions or billions of times the mass of the Sun. One of the giants lurking at the centers of galaxies. Our Milky Way has a supermassive black hole at its center called Sagittarius A star, pronounced Sagittarius A star, about 4 million times the mass of the Sun. Its event horizon has a radius, the Schwarzschild radius, of about 12 million kilometers. That's about 17 times the radius of the Sun, smaller than the orbit of Mercury, but enormous by everyday standards. From a distance far from the black hole's sphere of influence, space looks normal. You can see stars, galaxies, the familiar cosmos. But as you get closer, things start to change. You notice the stars behind the black hole distorting, their light bending around the curved space-time. You see multiple images of the same stars, stretched and warped into strange patterns, creating an optical effect called gravitational lensing. Directly behind the black hole, you see a ring of light, the photon sphere, where photons orbit the black hole. Some have orbited once, some twice, some many times, creating nested rings of increasing brightness. It's a region at about 1.5 times the Schwarzschild radius where light itself can orbit, though the orbits are unstable. Closer still, and the black hole reveals itself as a perfect circle of darkness, surrounded by that luminous photon ring. Any light that crosses the event horizon is gone forever, never to return, so the black hole appears as an absolute void, a hole cut out of the star field, a region of perfect blackness. The event horizon of this supermassive black hole has a radius of about 12 million kilometers. It's huge. You could fit several suns inside, but still tiny compared to the distances between stars. And time starts behaving strangely. You have a friend watching from a safe distance far from the black hole, outside its sphere of influence, perhaps 100 Schwarzschild radii away. You wave to them. They wave back. The signals take some time to travel, but everything seems normal. But as you fall closer to the event horizon, you notice their movements seem to speed up. From your perspective, falling toward the black hole into stronger and stronger gravity, time in the outside universe appears to run faster. Hours pass for them in what feels like minutes to you. If you could fall all the way to the horizon while somehow surviving and looking outward, you'd see the entire future history of the universe flash by in fast forward. Stars would be born and die. Galaxies would collide and merge. The universe would age billions of years while you fell. From their perspective, watching you, the opposite happens. You appear to slow down. Your movements become sluggish. The light from your ship becomes redder, shifted toward longer wavelengths by the extreme curvature of spacetime. This is called gravitational redshift and tilation, extreme version of the gravitational time dilation we talked about earlier. You get closer to the horizon, and to them, you slow further. Redder, dimmer, slower. You never quite cross from their perspective. You freeze at the edge, asymptotically approaching the horizon, but never quite reaching it. Your image fading to black as the light becomes infinitely red-shifted, stretched and frozen forever at the boundary. Both perspectives are true. This is one of the most mind-bending aspects of relativity. There's no single, correct viewpoint. You fall through and experience crossing the horizon in finite time. They see you stop and fade at the edge, never crossing. Both are valid descriptions of what happens, measured in different reference frames. This is one of the deepest lessons of relativity. Reality depends on perspective. Different observers moving differently or in different gravitational fields experience different versions of now, different flows of time, different simultaneous events. From your perspective, falling toward this supermassive black hole, you reach the event horizon in finite time. Maybe a few hours of proper time, depending on your trajectory and how fast you're falling. You don't feel anything special as you cross. You don't see a warning sign, don't hit a wall, don't feel a jolt or boundary. You just cross it. Space looks strange, the stars above you compressed into a shrinking circle, the blackness ahead growing, the view behind distorted by extreme curvature. But you're fine, at least in this large black hole. The tidal forces near the horizon are gentle because the event horizon is so large and the gravitational gradient is relatively shallow. But to your friend watching from outside, you never cross. You just get slower and dimmer and redder until you fade from view. They could watch for billions of years, could watch until the heat death of the universe, and never see you actually cross the horizon. This leads to a deep puzzle in black hole physics. If everything from the outside perspective takes infinite time to cross the horizon, how can black holes ever form? From the outside, doesn't the collapsing star also freeze at its own forming event horizon? The answer is subtle, yes. From the outside perspective, the surface of the collapsing star appears to freeze just outside where the horizon would be. But that surface becomes darker and darker, red-shifted to longer and longer wavelengths, effectively disappearing from view in a fraction of a second. For all practical purposes, the black hole has formed, even though from the outside perspective, matter is still technically approaching the horizon. Inside the event horizon, the rules change in a profound and unsettling way. Space and time swap roles. Outside the horizon, you can move in space, left, right, forward, back, but you can't move backward in time. Time's arrow points one direction, forward into the future. You can choose where to go in space, but you can't choose where to go in time. Time carries you forward whether you like it or not. Inside the horizon, this swaps. The singularity is not a place in space that you can avoid by going left or right. It's a moment in time, a moment in your future. Just as you can't stop moving forward in time outside the horizon, inside the horizon, you can't stop moving inward in space toward the singularity. It's not that there's a force pulling you in. It's not that the black hole is sucking you toward the center, it's that all possible paths through space-time, all possible futures, all geodesics lead to the singularity. There is no trajectory, no amount of rocket thrust, no clever maneuver that can take you away from it. Your future ends at the singularity. Imagine you're driving on a road and someone tells you, "Don't arrive at next Tuesday." That's impossible. Time moves forward and next Tuesday will come whether you want it to or not. You can't avoid it by turning left, right, or stopping. It's a moment in your future, not a place in space. Inside a black hole, the singularity is like next Tuesday. It's not a place you can avoid by changing direction. It's a moment in your future that you can't avoid, that's coming inexorably. That defines the end of your world line. And here's where things get really extreme. As you fall toward the singularity, even in a large black hole, the tidal forces eventually become significant. Tidal forces are differences in gravitational pull across an object. Your head being pulled more strongly than your feet because it's closer to the mass, creating the gravity. Near Earth, tidal forces are negligible on human scales. The difference in gravitational pull between your head and feet is utterly tiny. Near a neutron star, tidal forces would be enormous. You'd be stretched vertically and compressed horizontally long before reaching the surface. Near a stellar mass black hole, say 10 times the Sun's mass with an event horizon radius of about 30 kilometers, tidal forces at the horizon would already be lethal. You'd be torn apart before you crossed, stretched into a long, thin strand of atoms. This process has a technical name in astrophysics: spaghettification. Yes, really, that's the actual term physicists use. But in our supermassive black hole with its enormous event horizon, tidal forces at the horizon are gentle. The gravitational gradient is shallow. You could cross and survive, at least for a while. How long do you have between crossing the event horizon and reaching the singularity? It depends on the mass of the black hole and your trajectory. For a black hole 4 million times the Sun's mass, like Sagittarius, a star, you'd have perhaps 10 to 20 seconds. For even larger black holes, billions of solar masses, you might have minutes or even hours. What would you see in those final moments? Looking up toward the event horizon, you'd see the entire outside universe compressed into a shrinking circle. Above you, time-lapsed, centuries or millennia passing in seconds. The stars would move through their orbits, novae would flash, galaxies would evolve. Looking down, toward the singularity ahead of you in time, you'd see, we don't know, the light from other infalling matter perhaps, extreme distortions. And eventually, as you approach the singularity, the tidal forces would grow without limit. What happens at the singularity? We don't know. Our equations break down completely. General relativity predicts infinite curvature, infinite density, infinite tidal forces, a point where the laws of physics as we know them cease to have meaning. The equations give us infinities, and in physics, infinity is usually nature's way of telling us we've reached the limits of our theory, that we're missing something, that we need new physics. And that's the problem. Einstein's theory works beautifully almost everywhere. It predicts the orbits of planets with exquisite precision, including Mercury's. Extra precession. It predicts the bending of light, the slowing of time, the existence of black holes, the expansion of the universe. In 2015, the LIGO detectors detected gravitational waves, ripples in space-time itself, from two black holes spiraling together and merging 1.3 billion light-years away. The signal matched Einstein's century-old predictions with stunning precision, including every detail of the frequency evolution, amplitude, and final ringdown as the merged black hole settled. Since then, we've detected dozens more black hole mergers and neutron star mergers, each one confirming general relativity in the most extreme conditions we can observe. But at the singularity and in other extreme situations like the very first moments of the Big Bang, general relativity fails. It breaks down. It gives meaningless answers. And that's because gravity, as Einstein described it, smooth and continuous and geometric, cannot be the whole story when quantum mechanics enters the picture. We have two great theories that describe the universe. General relativity describes the large, planets, stars, galaxies, black holes, the curvature of space-time, gravity itself, the evolution and fate of the entire cosmos. Quantum mechanics describes the small, atoms, electrons, photons, quarks, the probabilistic dance of particles at the tiniest scales, the fundamental forces that hold matter together and drive nuclear reactions. Both theories work. Both have been tested extensively, subjected to experiment after experiment, prediction after prediction, scrutinized in every way imaginable, and both match reality with extraordinary, almost absurd precision. General relativity predicted gravitational waves, ripples in space-time propagating at the speed of light, in 1916. We detected them for the first time in 2015, exactly as predicted. The LIGO discovery confirmed Einstein's theory in one of the most extreme environments. Two black holes, each about 30 times the mass of the Sun, spiraling together at half the speed of light and merging in a collision that released more power than all the stars in the observable universe combined for a fraction of a second. The signal, a chirp rising in frequency and amplitude over a tenth of a second, matched Einstein's predictions to extraordinary precision. Since then, dozens more gravitational wave events have been detected from merging black holes and neutron stars, each one confirming general relativity. Quantum mechanics predicts the energy levels of hydrogen atoms to 12 decimal places. It predicts the magnetic moment of the electron to 11 decimal places, one of the most precisely verified predictions in all of science. It explains why some materials conduct electricity and others don't, why the sun shines, why atoms don't collapse, why you can't walk through walls, why chemistry works the way it does. The entire digital revolution, computers, smartphones, the internet, LED lights, solar panels, MRI, machines, lasers, transistors, everything is built on quantum mechanics. Every device you use relies on our understanding of quantum physics. The theory works spectacularly well. There's just one problem. They contradict each other. Quantum mechanics says that at the smallest scales, everything is uncertain, probabilistic, discrete. Energy comes in packets, quanta. Particles exist in superpositions, multiple states at once until measured. You can't know both position and momentum precisely. This is the Heisenberg uncertainty principle. The universe is fundamentally grainy at the tiniest levels, governed by inherent randomness and probability waves. General relativity says that space-time is smooth, continuous, deterministic. Curvature is gradual and precise, described by differential equations. Cause and effect are clear. Given the distribution of matter and energy at one moment, Einstein's equations determine the curvature of space-time and the evolution of the universe exactly, with no randomness. Both can't be completely right, not in their current forms. They describe the universe in fundamentally incompatible ways. They use different mathematical frameworks, different assumptions about the nature of reality. At everyday scales, this doesn't matter. The regimes don't overlap. If you're calculating the orbit of a planet, you use general relativity and ignore quantum mechanics. The quantum uncertainty in a planet's position is utterly negligible, about 10 to the power of minus 60 meters, far smaller than an atomic nucleus. You get the right answer. If you're calculating the behavior of an electron in an atom, you use quantum mechanics and ignore gravity. The gravitational force between an electron and a proton is about 10 to the power of 40 times weaker than the electromagnetic force. Gravity is utterly negligible. You get the right answer. The problems only appear when you try to combine them, when you look at situations involving both extreme gravity and quantum scales. Like the singularity, inside a black hole where all the mass is compressed into a volume so small, smaller than an atom, smaller than a nucleus, approaching the Planck length of 10 to the power of minus 35 meters. That quantum effects must become important. What happens when you try to apply quantum mechanics to something with the density of a black hole singularity? The theory breaks. Quantum field theory, applied to curved spacetime with extreme curvature, gives infinities and nonsensical results. Or the first moments of the Big Bang, when the entire observable universe, everything we can see, billions upon billions of galaxies spanning 93 billion light-years, was compressed into a space smaller than an atom. At that moment, 13.8 billion years ago, both quantum uncertainty and gravitational curvature were enormous. In these places, space-time is curved so sharply at such small scales that quantum effects can't be ignored, and our theories break. We get infinities, contradictions, results that make no sense. We need a theory of quantum gravity, a way to describe how space-time itself behaves at the smallest scales, how gravity emerges from or connects to the quantum world, how the smooth fabric of general relativity fits with the grainy, probabilistic nature of quantum mechanics. Physicists have been trying to find this theory for nearly a century. Since the 1930s, the brightest minds in physics have attacked this problem from every conceivable angle. And we still don't have the answer. Some approaches propose that gravity, like the other forces of nature, is mediated by particles. We know that electromagnetic force is carried by photons. When two electrons repel each other, they do so by exchanging virtual photons. Quantum particles that exist briefly, carry the force, then disappear. The weak nuclear force is carried by W and Z bosons. The strong nuclear force is carried by gluons. Perhaps gravity is carried by particles called gravitons, hypothetical quantum messengers of space-time curvature. The mathematics of quantum field theory suggests gravitons should exist. They should be massless, travel at the speed of light, have a property called spin 2, related to how they transform under rotations, and interact incredibly weakly with matter, much more weakly than any other particle. But we've never detected one, and we likely never will with any conceivable technology. The gravitational force is so weak compared to other forces that detecting a single graviton would require a detector with the mass of Jupiter operated for billions of years. Even then, you'd only detect one graviton occasionally. They remain purely theoretical, predictions of a theory we haven't fully constructed. And there's a deeper problem. When physicists try to build a quantum theory of gravity using the same methods that worked brilliantly for the other forces, the methods of quantum field theory, they run into infinities. The calculations blow up, giving infinite results that can't be removed through the usual mathematical tricks that work for other forces. This suggests that gravity might be fundamentally different from the other forces, that it might require a completely new approach, a different framework entirely. That's where string theory comes in, perhaps the most famous and controversial attempt at quantum gravity. String theory proposes that fundamental particles aren't points, but tiny one-dimensional strings, loops, or open strands, vibrating in different patterns. Different vibration patterns correspond to different particles. An electron is one vibration mode, a quark is another, a photon yet another, and yes, A graviton emerges naturally as a particular vibration of a closed string loop. The mathematics is beautiful, elegant, and extraordinarily complex. String theory potentially unifies all the forces of nature, including gravity, into one framework. It's sometimes called a theory of everything. But the equations only remain mathematically consistent if spacetime has not 4 dimensions, 3 of space, 1 of time, but 10 or 11 dimensions. The extra 6 or 7 dimensions would be curled up, compactified at scales so small we can't see them, perhaps at the Planck length, about 10 to the power of minus 35 meters, about 10 to the power of 20 times smaller than a proton, far beyond anything we can probe with current or foreseeable technology. Imagine an ant walking on a garden hose. From far away, the hose looks one-dimensional, just a line. But to the ant walking on it, the hose has a second dimension. It can walk around the hose's circumference. That second dimension is curled up, too small to see from a distance, but it's there. String theory suggests our universe is like that. 3 dimensions are large and obvious. We move through them every day. 6 or 7 others are curled up so small that we can't perceive them, but they're there, and their precise geometry determines which particles and forces exist in our universe. Different ways of curling up the extra dimensions, different compactifications, lead to different physics, different particles, different forces. There might be an enormous number of possible compactifications, perhaps 10 to the power of 500 or more, each corresponding to a different possible universe with different laws of physics. String theory has produced fascinating insights into mathematics and theoretical physics. It's given us new ways to think about black holes and entropy, about the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary, like a hologram. It's revealed deep connections between quantum mechanics and geometry. But here's the fundamental problem. So far, string theory hasn't made testable predictions that would distinguish it from other approaches or confirm that it actually describes our universe. The energy scales where string effects would become noticeable are so high, near the Planck energy, about 10 to the power of 19 billion electron volts, that we can't reach them with any conceivable particle accelerator. The Large Hadron Collider, the most powerful accelerator ever built, reaches energies of about 10 to the power of 13 electron volts. To probe string scales, we'd need an accelerator the size of the galaxy, requiring more energy than humanity has ever produced. String theory remains a promising mathematical framework, elegant and fascinating, but without empirical verification. We don't know if it describes our universe or just a beautiful mathematical structure. Loop quantum gravity takes a different approach. Instead of starting with particles and trying to make gravity fit, it starts with general relativity, with geometry and space-time, and tries to make it quantum. Loop quantum gravity suggests space-time itself is made of discrete chunks, tiny loops of space woven together at the Planck scale, about 10 to the power of minus 35 meters. Space-time would be grainy, pixelated, quantized, like a digital image when you zoom in far enough. Space wouldn't be infinitely divisible. You couldn't subdivide it indefinitely. At the Planck scale, you'd hit a fundamental limit, the smallest possible unit of space, a quantum of space itself. This would resolve some of the infinities that plague attempts to quantize gravity. If space itself is discrete, some of the mathematical problems involving infinitely small distances go away. Loop quantum gravity makes different predictions than string theory about what happens at the center of a black hole. Instead of a singularity with infinite density, loop quantum gravity suggests the collapse stops at extremely high but finite density. perhaps 10 to the power of 94 grams per cubic centimeter, and the black hole might bounce, the collapse reversing into expansion, creating a new expanding region of space-time on the other side. Some versions suggest that what we call the Big Bang might actually be a big bounce, the collapse of a previous universe reaching maximum density and rebounding to create our expanding universe. But like string theory, loop quantum gravity hasn't made testable predictions that would allow us to confirm or refute it with current technology. The effects it predicts occur at scales far too small to observe directly. There are other ideas, other approaches. Causal set theory, which suggests spacetime is fundamentally made of discrete events, points in spacetime, connected by causal relationships, which events can influence which other events. And continuous spacetime emerges from this discrete web of causality. Emergent gravity theories, which propose that spacetime and gravity aren't fundamental at all, but emerge from something deeper, something more basic, the way temperature and pressure emerge from the motion of molecules, or the way the flow of water emerges from the behavior of H2O molecules. Some physicists, notably Eric Verlinde, suggest that gravity might emerge from entropy, from the thermodynamic tendency of systems to maximize disorder. In this view, what we experience as gravitational force is actually the result of space-time trying to maximize its entropy. Others think entanglement, quantum connections between particles, might be more fundamental than space-time, and that space-time geometry emerges from patterns of quantum entanglement. But none have succeeded yet. None have produced a complete, testable, experimentally verified theory that unifies gravity with quantum mechanics in a way that makes predictions we can check. This is the frontier, the cutting edge, the boundary of human knowledge. We know gravity shapes the cosmos at the largest scales. We know it's the curvature of space-time. We know it bends light, slows time, creates black holes, drives the expansion of the universe, produces gravitational waves. But we don't know what it is at the deepest level. We don't know how it emerges from or connects to the quantum realm. We don't know if space-time is fundamental or if it's made of something else, something more basic that we haven't discovered yet. Some physicists think the answer will require a complete rethinking of what we mean by space and time. Maybe they're not fundamental concepts. Maybe they're emergent properties, useful descriptions at large scales but not truly basic. The way north and south are useful on Earth's surface but become meaningless at the poles, or the way temperature is useful for describing a gas but doesn't apply to individual molecules. Maybe the question, what is gravity, is like asking, what is wetness, at the molecular level. Water molecules aren't wet. Wetness emerges when you have trillions of them together, interacting in specific ways. Maybe space-time and gravity emerge from some quantum substrate we don't yet understand, from information or entanglement or something we haven't even conceived of yet. And here's the beautiful, humbling truth. That's okay. Science isn't about having all the answers. It's never been about reaching a final theory and declaring victory. It's about asking better questions, refining our understanding, peeling back layers of mystery to reveal deeper mysteries. Always pushing forward, always exploring. Every generation of scientists stands on the shoulders of those who came before. Galileo studied falling objects and pendulums, discovering that all objects fall at the same rate regardless of mass, a crucial insight that contradicted Aristotle. Newton built on that work to create a universal law of gravitation, uniting heaven and earth. Einstein built on Newton to show that gravity is curved spacetime, overthrowing the absolute space and time of classical physics. The next breakthrough will build on Einstein. Maybe it's already happening. Maybe someone right now, a graduate student staying up late in a university library, a researcher analyzing data from a particle accelerator, a mathematician working on abstract equations at a blackboard, is on the verge of seeing something no one else has seen, making a connection no one else has made, asking the right question in the right way. Maybe the answer will come from the Large Hadron Collider at CERN, smashing protons together at 99.9999999% the speed of light, and seeing something unexpected in the spray of particles, a hint of extra dimensions, a signature of quantum gravity, a new particle that doesn't fit our theories. Maybe it will come from gravitational wave detectors like LIGO and Virgo, measuring the ripples in space-time from colliding black holes and neutron stars with increasing precision, finding tiny deviations from Einstein's predictions that point toward quantum corrections. Maybe it will come from observations of the cosmic microwave background radiation, the afterglow of the Big Bang, finding subtle patterns that reveal quantum effects in the early universe, quantum fluctuations in space-time itself that were stretched to cosmic scales. Maybe it will come from black hole observations with the Event Horizon telescope and its successors, imaging black hole shadows with increasing resolution, finding evidence of quantum effects near the horizon. Maybe it will come from pure mathematics, someone spotting an elegant pattern that everyone else has missed, a hidden symmetry or structure that unifies the equations of quantum mechanics and general relativity in a new way. A mathematical insight that opens doors no one knew existed. Or maybe, and this is the most exciting possibility, the answer will be something completely unexpected. A revolution as profound as quantum mechanics or relativity. Something that changes how we think about reality itself at the most fundamental level. Something we can't even imagine yet because we're missing a crucial concept or insight. The way people before Einstein couldn't imagine curved space-time or time dilation. That's happened before. Before quantum mechanics, physicists couldn't conceive that energy came in discrete packets, that particles could be waves, that uncertainty was built into nature. Before relativity, they couldn't imagine that time could slow down, that space could curve, that simultaneity was relative. The next breakthrough might be equally strange, equally counterintuitive, equally transformative. And somewhere out there in the mathematics we haven't explored, in the experiments we haven't done, in the questions we haven't asked, that breakthrough is waiting. But while we wait for it, while the frontiers of physics push forward into the unknown, let's step back and remember something important. We live in this universe. We're shaped by gravity every single day. And even without understanding its deepest nature, we can appreciate what it means for us, for life, for everything we know and love. Let's come back to Earth. You're still here reading this, held gently to the surface of a spinning planet by the curve of space-time. Every breath you take, every step you make, every moment of your existence is shaped by gravity. But it's more than that. Gravity is the reason anything exists at all. Go back 13.8 billion years to the moments after the Big Bang. The universe is expanding rapidly, cooling as it expands, filled with hydrogen and helium gas, the simplest elements forged in the first 3 minutes after the Big Bang, when the entire observable universe was as hot and dense as the core of a star. This gas is spread almost uniformly throughout space. Almost, not quite. There are tiny fluctuations, quantum fluctuations from the very earliest moments, from the first 10 to the power of minus 35 seconds, when the universe was smaller than an atom, amplified by cosmic inflation to cosmic scales and frozen into the fabric of space. Regions where the gas is just slightly denser than average. Differences of maybe 1 part in 100,000. Tiny. Barely noticeable if you were there. but enough. And gravity amplifies those differences. The denser regions pull in more gas from their surroundings. As they grow denser, their gravity grows stronger. They pull in even more. The rich get richer. The dense regions become denser, the sparse regions become sparser. A positive feedback loop driven by gravity. Over millions of years, these small differences become enormous clouds of gas, hundreds of light years across, thousands of times more massive than our sun, collapsing under their own weight. The gas compresses as it falls inward. As it compresses, it heats. Gravity converts gravitational potential energy into thermal energy, the same principle that makes a bicycle pump warm when you compress air. Eventually, after millions of years of collapse in the cores of these clouds, temperatures reach 10 million Kelvin. At these temperatures, hydrogen nuclei are moving fast enough that when they collide, they can overcome their electromagnetic repulsion. Both positively charged, they normally push apart and fuse together, releasing energy. Nuclear fusion ignites. A star is born. Gravity creates stars, and stars create everything else. Inside stellar cores, gravity compresses matter to temperatures and pressures where nuclear fusion occurs, building heavier elements from lighter ones through a process called nucleosynthesis. Hydrogen fuses into helium. That's what makes stars shine, converting about 0.7% of the mass into energy according to E equals mc squared. In more massive stars, helium fuses into carbon and oxygen. Carbon fuses into neon, magnesium, silicon. Silicon fuses into iron. Every element in the periodic table heavier than helium, carbon, nitrogen, oxygen, iron, gold, uranium, everything, was forged in the core of a star or in the explosion of a dying star. You are made of star stuff. This isn't poetry, it's literal truth. This isn't metaphor, it's documented nuclear physics. The calcium in your bones, forged in a star. The iron in your blood that carries oxygen to your cells, forged in a star, probably in the final moments before it exploded. The oxygen you're breathing right now, forged in a star. The carbon that forms the backbone of every organic molecule in your body, forged in a star. When massive stars exhaust their nuclear fuel and explode as supernovae, they scatter these elements into space at thousands of kilometers per second. The explosion, powered by gravitational collapse, releases more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. And gravity pulls that enriched material together again into new clouds, new stars, new planetary systems. Our solar system formed from such a cloud about 4.6 billion years ago. A previous generation of stars had lived and died, enriching the interstellar medium with heavy elements. Gravity pulled that material, mostly hydrogen and helium, but about 2% heavier elements, into a new cloud. The cloud collapsed. Gravity pulled most of the mass into the center, creating enough pressure and temperature to ignite nuclear fusion, forming the sun. The remaining material formed a rotating disk around the young sun. In that disk, gravity pulled dust particles together into larger clumps. Clumps collided and stuck together, growing into larger bodies. Over millions of years, these grew into asteroids, then planetesimals, then planets. Gravity gave Earth its spherical shape, the only shape where every point on the surface is equidistant from the center, the lowest energy configuration for a self-gravitating body. Smaller asteroids can be irregularly shaped because their gravity is weak, but anything larger than about 400 kilometers in diameter is pulled into a sphere. Gravity separated Earth into layers. The densest material, iron and nickel, sank to the center, forming the core. Lighter silicate rocks floated on top, forming the mantle and crust. This process, called differentiation, was driven by gravity. Gravity created the pressure that keeps Earth's interior hot even 4.6 billion years after formation. The weight of overlying rock compresses the interior, and compression generates heat. Combined with heat from radioactive decay, this keeps Earth's interior molten. That heat drives plate tectonics, the motion of continents, the formation of mountains, the creation of volcanoes and earthquakes. Plate tectonics, in turn, recycles carbon dioxide from the atmosphere into rocks and back out through volcanoes, regulating Earth's climate over geological timescales, preventing runaway heating or cooling. Without gravity, without plate tectonics, Earth's climate might have gone wildly off course like Venus, too hot, runaway greenhouse effect, or Mars, too cold, atmosphere lost to space. Gravity in Earth's liquid iron outer core, combined with the planet's rotation, generates electric currents through a process called the dynamo effect. These currents create Earth's magnetic field, which extends tens of thousands of kilometers into space, creating the magnetosphere. The magnetosphere deflects the solar wind, the stream of charged particles flowing from the sun at hundreds of kilometers per second. Without the magnetic field, the solar wind would gradually strip away Earth's atmosphere over millions of years, the way it stripped away much of Mars's atmosphere after Mars lost its magnetic field about 4 billion years ago, when its core cooled and solidified. Gravity holds our atmosphere. Air molecules move at thermal velocities, hundreds of meters per second at room temperature, but Earth's escape velocity is 11.2 kilometers per second. Gravity keeps most atmospheric molecules from escaping into space. The Moon, with its weaker gravity, 1/6 of Earth's, couldn't hold on to its thin, early atmosphere. Mercury, despite being hotter, has virtually no atmosphere because its escape velocity is only 4.3 kilometers per second, and its small mass doesn't gravitationally bind gases effectively. Gravity creates tides. The Moon and Sun pull on Earth's oceans and on Earth itself, creating bulges. The side of Earth facing the Moon is pulled more strongly than Earth's center, and Earth's center is pulled more strongly than the far side. This creates two bulges, one facing the Moon and one opposite. And as Earth rotates beneath these bulges, we experience high tide twice daily. These tides may have been crucial for life's origins. Many scientists think life began in tidal pools, where cycles of wetting and drying could concentrate organic molecules, drive chemical reactions without enzymes, form the first membrane-enclosed protocells. Gravity keeps the Moon in orbit at an average distance of 384,000 kilometers, and the Moon, in turn, stabilizes Earth's axial tilt through gravitational interactions. Without the Moon, Earth's rotation axis would wobble chaotically over millions of years due to gravitational perturbations from other planets, swinging from nearly upright to severely tilted. This would create wild climate swings, ice ages alternating with hot periods on timescales too rapid for complex life to adapt. With the Moon, Earth's tilt stays stable at about 23.5 degrees, giving us predictable seasons, a stable climate over millions of years, conditions where complex life can evolve and persist. Gravity holds the Sun together, maintaining the nuclear furnace at its core that's burned for 4.6 billion years and will continue for another 5 billion. The Sun's core reaches 15 million Kelvin and 250 billion atmospheres of pressure, conditions where hydrogen nuclei fuse into helium at a rate of about 600 million tons per second, releasing the energy that eventually reaches Earth as sunlight. Every meal you've ever eaten traces back to that sunlight. Plants capture photons through photosynthesis. converting carbon dioxide and water into sugar and oxygen using light energy. Animals eat plants or eat other animals that ate plants. The entire food chain is powered by sunlight, which exists because gravity compresses the sun's core. Even fossil fuels, coal, oil, natural gas, are ancient sunlight, stored chemical energy from organisms that lived hundreds of millions of years ago. You are here because of gravity. Life is here because of gravity. The atoms in your body, the air you breathe, the ground beneath your feet, the warmth of the sun, the light of the stars, the stable climate, the recycled nutrients, the magnetic shield. All of it exists because space-time curves around mass, because objects follow that curve, because the universe is woven together by this one elegant, mysterious rule. Think about that for a moment. The same phenomenon that makes an apple fall from a tree is responsible for the existence of stars, the synthesis of heavy elements, the formation of planets, the origin of life, and ultimately, you. The curvature of space-time near Earth keeps you on the ground, makes your heart work to pump blood upward, shapes your skeleton, governs every motion you make. The curvature of space-time around the sun keeps Earth in orbit at just the right distance for liquid water to exist, neither too close, too hot, nor too far, too cold. In the habitable zone where life can flourish, the curvature of space-time in collapsing gas clouds creates stars that forge elements and produce light. The curvature of space-time across the entire universe shapes galaxies into vast cosmic webs. Galaxies clumped along filaments billions of light-years long, with enormous voids in between, all shaped by gravity acting on the initial quantum fluctuations from the Big Bang. One rule, one phenomenon, operating at every scale from the fall of a raindrop to the structure of the cosmos. And here's the most beautiful part. You are made of the universe. You're not separate from it, not an isolated observer standing outside looking in. You're part of the fabric. Your mass curves space-time too. Right now, the atoms in your body are creating tiny ripples in the shape of space, infinitesimally small, but real, predicted by the same equations that describe black holes and galaxies. If you could see space-time curvature, you'd see that you create a tiny dip in the fabric around you, just like Earth creates a larger dip, just like the sun creates an even larger one. The difference is scale, not kind. You're made of the same stuff, following the same rules. You're connected to everything around you through the geometry of the cosmos itself. When you walk, you're navigating through curved space-time. Your muscles push against the ground, and the ground pushes back with a force equal to your weight, accelerating you upward at 9.8 meters per second squared, preventing you from following your geodesic through the curved geometry created by Earth's mass. When you look at the stars, you're seeing light that has traveled across a curved universe, bent and shaped by every massive object it passed: galaxies, dark matter clumps, galaxy clusters. The photons entering your eyes have followed geodesics through dynamic shifting space-time, a journey that began perhaps thousands or millions or billions of years ago in the atmosphere of a distant star. When you feel the pull of Earth beneath your feet, you're experiencing the curvature of space-time itself, the fundamental geometry of reality, the shape of the four-dimensional fabric we're all embedded in. And no one, not Newton, not Einstein, not the greatest minds working today, has fully understood it at the deepest level. We know what it does. We can predict its effects with remarkable precision, guiding spacecraft across billions of kilometers. Timing GPS satellites to nanoseconds, detecting gravitational waves from events billions of light-years away. But what it is at the deepest level, whether space-time is fundamental or emergent, whether it's continuous or discrete, how it connects to quantum mechanics, that remains one of the great mysteries. And that's beautiful too. So, where does that leave us? We've traveled together on a remarkable journey from falling apples to curved space-time, from Newton's equations to Einstein's geometry, from the surface of Earth to the event horizons of black holes, from the quantum realm where our theories break down to the vast cosmic web shaped by gravity across billions of light years. We've learned that gravity isn't what our intuitions suggest, isn't what thousands of years of human experience led us to believe. It's not a force reaching across empty space, pulling objects together with invisible hands. It's the shape of space-time itself, the geometry of reality, curved by the presence of mass and energy, defining the paths that everything, matter, energy, light, follows through the four-dimensional fabric of the universe. We've learned that mass tells space-time how to bend, and space-time curvature tells matter how to move. That objects in orbit, the moon around Earth, Earth around the sun, stars around the galaxy, galaxies around each other, aren't being held by invisible chains. They're following straight-line paths, geodesics, through curved four-dimensional geometry. We've learned that when you stand on Earth, you're not being pulled down by a mysterious force. You're being pushed up by the ground beneath you, accelerating upward at 9.8 meters per second squared, prevented from following your natural geodesic, your natural path through curved space-time. We've learned that gravity bends light, turning galaxies and galaxy clusters into cosmic telescopes, creating halos and rings and multiple images of distant objects, revealing the distribution of dark matter through gravitational lensing effects. We've learned that gravity bends time itself, that clocks run at different rates depending on how deep they are in a gravitational well, that your head ages microscopically faster than your feet, that near extreme masses like neutron stars or black holes, time can slow dramatically while the universe outside ages normally. We've learned that black holes exist, places where space-time curves so sharply that even light cannot escape, where the future inevitably leads to a singularity, where time and space swap roles, where our best theories break down and give us infinities instead of answers. And we've learned, perhaps most importantly, that we still don't know everything, that at the smallest scales and the most extreme conditions, at black hole singularities in the first moments of the Big Bang, our best theories, general relativity and quantum mechanics, give different, incompatible answers, and we don't yet know how to reconcile them, how to merge the smooth geometry of space-time with the grainy quantum world. But maybe that's the most important lesson of all. Science is not a collection of final answers etched in stone, not a destination we reach and then stop. It's a process, an ongoing conversation between humanity and the universe, where we ask questions and nature responds, sometimes with clear answers, sometimes with hints and riddles, sometimes with new questions we never thought to ask, always leading us deeper. Every generation builds on what came before, standing on the shoulders of giants, seeing farther because of those who came before. Aristotle thought objects fell because they sought their natural place, a teleological explanation that satisfied human intuition. That idea held for 2,000 years, explaining everyday observations but missing the deeper universal pattern. Newton showed that gravity is universal, connecting earth and sky under one mathematical law, explaining both falling apples and orbiting moons with the same inverse square relationship. That insight revolutionized physics and held for 2 centuries, making accurate predictions, guiding astronomers and engineers, enabling the scientific revolution. Einstein revealed that gravity is geometry, that space and time are woven together into a dynamic fabric, that mass curves the fabric of reality and objects follow that curvature. That understanding has held for Over a century now, tested in every way we can imagine, from GPS satellites to gravitational wave detectors, and it keeps being right. Each answer was deeper, more fundamental, more strange and beautiful than the one before. Each revolution overturned what came before while preserving its successes. Newton's laws still work brilliantly for ordinary situations, and we still use them to navigate spacecraft through the solar system. Einstein's theory reduces to Newton's laws in weak gravitational fields and at low speeds. And somewhere ahead of us, there's another layer waiting to be discovered, another revolution that will overturn Einstein while preserving what works, explaining gravity at quantum scales, revealing what space-time is made of at the Planck scale, connecting the geometric and quantum descriptions of reality. Maybe space-time isn't fundamental, isn't the deepest level of reality. Maybe it emerges from something more basic, something quantum, something informational, something we haven't even imagined yet. Maybe gravity is a shadow, an echo, a projection of physics happening in dimensions or at scales or in frameworks we can't directly observe. Or maybe the answer is simpler than we think, hiding in plain sight. Maybe we're missing something obvious, something that will seem clear once someone points it out. The way Einstein's insights about falling elevators and curved spacetime seem obvious in retrospect, but were revolutionary at the time, transforming how we see reality. History teaches us that the next breakthrough often comes from an unexpected direction, from asking a question that seems naive or pursuing an idea that seems crazy. Quantum mechanics emerged from trying to understand why hot objects glow different colors. Special relativity emerged from puzzles about the speed of light and electromagnetic waves. General relativity emerged from thinking about a man falling off a roof. The breakthrough in quantum gravity might come from string theory or loop quantum gravity, or some approach that hasn't been invented yet, or from a combination we haven't imagined. It might come from a young physicist asking a naive question that exposes a hidden assumption everyone else has accepted without thinking, the way Einstein questioned the assumption that time flows at the same rate everywhere. We don't know. And that's not a failure, that's an invitation to explore, to question, to push forward into the unknown. The universe is stranger and more beautiful than we ever imagined, than we can imagine. Every mystery we solve reveals depths we never suspected. Every answer leads to new questions, new frontiers, new wonders waiting to be discovered. Think about where we've come in just a few centuries, in the blink of an eye compared to human history. From thinking the Earth is flat and stationary at the center of creation, to knowing we orbit a star in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, all expanding from a hot, dense state 13.8 billion years ago, carrying the evidence of its origin in the cosmic microwave background radiation that fills space. From thinking falling objects and orbiting moons are completely different phenomena, governed by different rules, operating under different principles, to understanding they're both following geodesics in curved spacetime, obeying the same geometric laws. From having no idea how the sun shines, why stars exist, where they get their energy, to understanding nuclear fusion, stellar evolution, the synthesis of elements, the life cycles of stars from birth in nebulae to death as white dwarfs, neutron stars, or black holes. From wondering what stars are made of, whether they're tiny nearby objects or distant suns, to measuring their composition better than we know Earth's deep interior, just by analyzing the light they emit through spectroscopy. And we did all of this by asking questions, making observations, building instruments, testing ideas, sharing discoveries, learning from failures, building on each other's work, generation after generation, creating the cumulative edifice of scientific knowledge. The next great breakthrough could come from anywhere, from anyone. From an unexpected particle at CERN's Large Hadron Collider or its successors. From an anomaly in gravitational wave signals detected by LIGO, Virgo, KGRA, or future space-based detectors. From a pattern in the cosmic microwave background that reveals quantum gravity effects. From a detailed observation of black hole shadows with the Event Horizon Telescope. From a mathematician noticing an elegant structure hidden in equations. From a student asking a question in class that no professor can fully answer. Science is a profoundly human endeavor, built by people, not perfect, idealized geniuses, but real people with doubts and struggles and moments of insight, people who make mistakes and learn from them, who collaborate and sometimes compete, who are driven by curiosity and wonder and the deep human desire to understand our place in the cosmos. And you're part of that story, whether you realize it or not. Every time you look up at the night sky and wonder how it all works, every time you question why things are the way they are, you're engaging in the same fundamental curiosity that drove Galileo and Newton and Einstein, and every scientist who came before and after them. Every time you question an assumption, every time you ask why or how, every time you refuse to accept "that's just the way it is" as a final answer, you're participating in humanity's greatest adventure. The quest to understand our place in the cosmos, to comprehend the rules that govern reality, to push back the boundaries of ignorance and illuminate the unknown. You're living in a cosmos where space and time are woven together into a dynamic, four-dimensional fabric, where the presence of matter and energy curves that fabric, where light bends and time slows and black holes lurk at the centers of most galaxies, where the same geometric rule connects everything from falling raindrops to spiral galaxies billions of light years across. You're living in a universe that we can describe mathematically with extraordinary precision, that we can predict with stunning accuracy, sending spacecraft to distant planets, detecting ripples in space-time from events billions of light years away. Yet we cannot fully explain at the deepest level, where elegant equations guide our technology but break down at singularities, where the same rule that holds you to Earth shapes the largest structures in the cosmos, where we've come so far but still have so far to go, and you're part of it, not just in it, part of it, woven into the fabric. The atoms in your body were forged in the cores of ancient stars that lived and died billions of years ago. Those stars exploded as supernovae, scattering their enriched material into space. Gravity pulled that material together into new clouds, new stars, our sun, a disk of dust around it that became planets. Geology and chemistry transformed rocks into an ocean, an atmosphere, the conditions for life. Evolution transformed simple molecules into cells, cells into complex organisms, organisms into you. A pattern of matter complex enough to contemplate its own existence. You are made of star stuff, as Carl Sagan eloquently said. Every atom in your body except hydrogen, and hydrogen makes up about 60% of your atoms and 10% of your mass, came from a star. You are the universe becoming conscious of itself, aware of itself, asking questions about itself, seeking understanding of the rules that govern it. The curve of space-time runs through you. You're not separate from the cosmos. You're woven into it, connected to everything by the same geometry that holds galaxies together and makes apples fall, part of an unbroken chain of causation stretching back to the Big Bang. So the next time you drop something, watch it fall. Really watch it, understanding what you're seeing. That object is following a geodesic through curved space-time. It's moving in the straightest possible line through a universe that isn't straight, through a four-dimensional geometry we can describe with equations but struggle to visualize. It's following the curvature created by Earth's mass, by the warping of the space-time fabric we're all embedded in. Feel the weight of your body, the press of the ground against your feet. That sensation is the ground accelerating you upward, pushing you up through curved space-time, preventing you from following your natural path through the geometry of reality. Look up at the moon, hanging in the sky, falling forever around Earth, never hitting, never escaping, held by the curve of space-time, orbiting because it's moving sideways as it falls, following a geodesic that loops around our planet month after month, year after year, for billions of years. Look at the stars, scattered across the night sky, each one a distant sun, many with their own planets. Their light has traveled across a curved universe, bent by every galaxy and black hole it passed, following geodesics through space-time, bringing you information from the past, from years ago for nearby stars, from thousands of years ago for distant stars, from millions or billions of years ago for distant galaxies. And remember, you're standing on a planet, orbiting a star, in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, all held together by a rule we can describe mathematically, test experimentally, apply technologically, but still don't fully understand at the deepest level. Gravity is the invisible architecture of everything. The reason stars shine and planets exist. The reason elements form and life arises. The reason you have ground beneath your feet, air to breathe, and a sun to warm you. The reason we're here to ask questions about it all. It's the geometry of space-time, the curvature of reality, the paths that objects follow when nothing pushes or pulls them, the shape of existence itself. And it's still teaching us, still surprising us, still showing us that reality is deeper, stranger, more interconnected, more beautiful, more wonderful than we ever imagined or can imagine. Newton gave us the mathematics, the inverse square law, the universal gravitation, the connection between heaven and earth, the unification that launched modern physics. Einstein gave us the geometry, the curved space-time, the equivalence principle, the understanding that gravity isn't a force but the shape of reality itself, that space and time are one fabric, dynamic and responsive to mass and energy. And the next chapter is still being written. The next revolution is waiting to be discovered. The deepest nature of gravity, its connection to the quantum world, what space-time is made of at the Planck scale, how geometry and quantum mechanics unite. These mysteries remain, calling to us from the frontier of knowledge. Maybe the answer will come from someone watching this right now. Maybe you. Maybe your curiosity will lead you to study physics, to work on these problems, to see the connection that everyone else has missed, to ask the question that opens new doors. Or maybe you'll never work in physics professionally, but you'll pass on that sense of wonder to someone else, a child, a student, a friend. You'll inspire someone, teach someone, show someone that the universe is knowable, that mysteries have solutions, that we can understand the cosmos we find ourselves in, that science is humanity's collective effort to comprehend reality. That's the universe's weirdest rule. Gravity isn't a force pulling us down. It's the shape of existence itself, the geometry we're all swimming in, the curvature that connects everything from atoms to galaxies, from the fall of an apple to the expansion of the cosmos. And we're still learning how it really works. The journey continues, the questions deepen, the mystery endures. And that's beautiful. That's what makes science exciting. That's what makes existence wonderful, not having all the answers, but the adventure of seeking them, the joy of discovery, the connection between generations of curious minds building on each other's work. The universe is not a puzzle to be solved once and put away. It's an infinite source of wonder, always revealing new layers, always surprising us, always inviting us deeper into understanding. Thank you for joining me on this journey through infinite science. Thank you for your curiosity, your attention, your willingness to grapple with strange ideas and counterintuitive concepts. Keep questioning, keep wondering, keep looking up at the stars and asking how it all works, why things are the way they are, what lies beyond our current understanding. The universe is vast, mysterious, stranger than we imagine and stranger than we can imagine, but it's also comprehensible, knowable, governed by rules we can discover through observation and thought and mathematics, through the scientific method refined over centuries. And somewhere out there, in the structure of space-time itself, in the quantum foam at the smallest scales, in the interplay between matter and geometry, in connections we haven't made and questions we haven't asked, the next great mystery is waiting to be solved. The universe is waiting for us to understand it deeper. And that adventure, that quest for knowledge and understanding, will never end. Each answer reveals new questions. Each horizon crossed reveals new horizons. Keep exploring, keep asking, keep wondering. Keep that sense of curiosity alive, that childlike wonder at the world, that drive to understand. The cosmos has infinite stories to tell, and you're part of the greatest story of all, the story of matter becoming aware, of the universe understanding itself, of consciousness arising from stardust and asking questions about its origin. Until next time, keep looking up, keep thinking deeply, and remember, you're not just in the universe, you're part of it, and that's the most wonderful thing of all.